Good morning, guys, and welcome to, I think we are in week 8. We're still continuing with chapter 38. We need to finish that. Okay. Chapter 38 and chapter 39 are actually, it's the same idea, except the first one, namely chapter 38, is that waves behaving as particles, namely photons, have momentum, and momentum is really something only particles are supposed to have. Remember, momentum is the mass of the particle times the velocity. But what happened in here is that to explain certain phenomena, we resolved to this idea that light is actually a particle, and it resolves that beautifully. And then chapter 39 deals with the problem backward, that particles behave like waves. Particles behave like waves. Namely, electrons, they have wavelength, okay, associated with their kinetic motion, with their kinetic energy. So the point being in here is, those are the two chapters, they're related to one another. As a matter of fact, the problems are similar in a sense, except one is going from wave to particle and the other one is from particle to wave. So what I'm planning to do then is to basically jump in right to chapter 39. And then when we meet for the applications, we're going to pick up certain problems from chapter 38, but mainly from chapter 39, because even chapter 39 has problems that include the photons, basically. That's the particles of light. So that's the plan. That way we will have them, and actually other textbooks, they use them both in the same chapter. So this is the idea. Sounds good, everybody?
Yes.
Okay. So let me, because in a sense also we are a little bit behind, so hopefully we catch up also. So let me share with you the screen. Are you guys looking at chapter 38, OneNote?
I think so.
Okay, very good. You think so? I hope that's right.
I'm pretty sure.
Okay, good.
I think so too.
Okay, very good. So this is where we left off last time. Let me just remind you what we did last time. That really triggered the photoelectric effect. It's a monochromatic beam, okay? Usually it's in the UV range, okay? Usually it requires high energy, most of the time. And what happened in this case, you free electrons. So it seems like there is enough energy in here to overcome the work function of that metal, so that the electrons now are floating near the cathode. So all you need to do now is apply a potential between the cathode and the anode, and these electrons all of a sudden find themselves on the other side, and you complete the circuit. And you should see the readings in here in the galvanometer. What it takes to stop this current in here, this current of charges, is the energy needed just to turn the last electron, if you wish, that has enough energy to overcome this potential to get to the anode, and that will basically kill it. So that is the stoppage voltage. People were puzzled by this phenomenon because of the fact that they increase the intensity as much as they do. For low frequencies, this will not happen. But for high enough frequency, at least there is a cutoff frequency where this happens, even for low intensity. And there was no delay to it. So it was puzzling because the energy of the photons, or at least waves, if they were waves, should be proportional to the brightness of the beam, basically the intensity of light. But that's not happening. Furthermore, it has to do with the frequency. It has nothing to basically shine bright light. But that's not what was going on. So Mr. Einstein immediately picked up on a formula that Mr. Planck came up with, namely that the energy of this photon is proportional to the frequency, and that's all the problem. And it's going, okay. Furthermore, the stoppage voltage is proportional to the frequency in accordance. What is the stoppage voltage? I think we did it at some point. Is in confirmation with the
You keep cutting out.
Sorry about
Yeah, he's gone.
Sorry about that. Can you guys hear me?
Yes, we can.
Yes.
Anyway, there is something in here wrong with Tuesdays. Every Tuesday, this thing happens. And it's not like this semester. It's been like this for forever. So anyway, so the point I was trying to make in here, and hopefully you guys got it, is that the stoppage voltage is proportional to the frequency, okay? And the ratio or the slope has to do with this constant that Mr. Planck has introduced, later on was named after him, of h over e, okay?
You're not sharing your screen.
I'm not showing the screen, sorry about that. I thought I was. Anyway, share. Okay, so this is the slope. It's h, so this is the stoppage voltage, and this is the slope as you draw the function, basically the voltage versus the frequency is going to be a function in here that has this this behavior, okay? Where the y-intercept in here is clearly a negative value. That is actually the stoppage voltage. And the line in here, as they increase the voltage, is a linear line. And the slope is this ratio of h over e. If somehow you can find e, which you can, using Millikan experiment that you guys are familiar with from previous classes, then since you find e, then all you have to do is find the h. The slope will give you h, that constant that Mr. Planck has thrown in a few years before, about 5 years earlier. And we're going to get into that in chapter 39, actually, on the Planck basically idea, and to how he introduced this constant h. Later on, it buried his name. So h is Planck's constant. H is 6.626 times 10 to the negative 34 joules second, okay? So it has units of action. So this is an action. The action is energy per unit time, basically, okay? So, so this constant in here appeared in here, and Mr. Einstein took advantage of it. So that was an experiment. Of course, that was puzzling. That was a major problem. How are we going to explain that? What is going on in here, okay? So there is no physics at that time to explain it. That's the problem. The second thing in here, because as I was explaining in here earlier, the whole experiment has to do with the intensity, and this has nothing to do with that. It has to do with frequency, okay? And the other thing that we discussed is how Mr. Rangan basically produced the X-rays and came up with an explanation for them using the fact that this fast-moving electrons now that are produced, they come to a standstill, and they should produce a wide array of rays, okay? What happened in here in the experimental observations, there is a cutoff wavelength in here, cutoff frequency. So we needed to explain that. And again, that has to do with the same relationship that we were talking about in here, okay? That too could only be explained by the fact that light is a particle with a momentum. Then we discussed the ideas since light has a momentum, of course, it has no mass. It's supposed to have a massless because it moves with the speed of light. And if it has mass, then we have a problem because remember, all of the expressions are something divided by gamma, okay, including the mass and the momentum, mv, well, not divided by gamma, multiplied by gamma, and gamma itself is square root of 1 minus v squared over t squared. Well, if v is equal to c, we have a problem because that's light. V is equal to c for light. Okay, so if you're a photon riding, if you're riding on the photon, your speed is exactly c. So that's the reference frame you're moving in. So this number will be 0, and you're dividing by 0. The only way that this can make sense for the momentum to have a finite momentum is the mass also goes to 0 because the velocity is c. So if this is c, then the only way to have a finite value is that you go back to the indetermination 0 over 0, and to resolve that, then you can come up with another way, namely the fact that the momentum p for this particle is h over lambda. Okay, so that is basically how we resolve this one. So the mass must be 0. Now we have a momentum, and the momentum is related to the energy through this expression. Okay, so that's basically in a nutshell what we did last time, and we're going to go to another experiment that was done in St. Louis, Missouri, actually in Washington University near Delmar Loop. I don't know if you know the area or not. Anybody is from the Midwest who know the area? No? Well, I live about half a mile from that city, from that campus, and we used to play soccer in it, so it was fun. Anyway, the point being here is that Mr. Compton in Washington University in 23 or 24, around that time, he did an experiment, okay? And that experiment basically involved those highly energetic waves that were produced in here, X-rays. And you have an X-ray. So this is the wave. So you have lambda, okay? So this lambda is very, very short, of the order of anywhere between a nanometer to a picometer, anywhere between 10 to the negative 9 meters to 10 to the negative 12 meters. Okay, so these are very, very short wavelength. And remember, light, the visible light, is between what is it, 700 nanometers to about 400 nanometers. This is the shortest you can get is the UV radiation. I'm not the UV, I'm sorry, this is the violet. And things below that are UV, okay? But this is even shorter. This is of the order of a nanometer, all the way to a picometer. So it's in this range. This is the red, this is the violet, and this is UV. So again, the experiments of Mr. For the photoelectric
Professor, you're cutting out again.
Sorry. Okay, if it goes back.
We still can't hear you.
Just restart it. Sorry about that. Okay. Anyway, this is the. So why is that? I was saying before. Okay. So anyway, so I don't know where we stopped right now, but let me see if I can pull it quickly in here. Share notes. So again, I was talking about the Compton scattering, and again, I have to go back and forth for it. And the experiment that Mr. Compton did was in the X-ray range, okay, in this range. So this is the photoelectric effect for the most part. And now we're talking about a new phenomenon. So Mr. Compton, when he did the experiment, he sent very high energy, very short wavelengths, okay, of the order of a nanometer to a picometer. Sounds good, everybody?
Yes.
Yes.
Okay, so imagine with me that there is a material in here. I think here under there's tungsten, where there are free electrons in here heated up. Okay, so the electrons are sitting in here, basically going on average nowhere, until one of them get hit by a photon, by this photon, basically this light beam, which is of a high frequency, in this case short wavelength. So what happened in this case is that the electron recoil in this direction. I'm going to call it phi e for the electron. Obviously, this is going to be inside the material. Okay, I'm just blowing it up, and then I can go and have a detector in here, sit in this direction, and find the beam that came up in here. Well, this came up with a different wavelength. So the wavelength of the light that came out is actually longer wavelength, less energy, if you wish. So what happened in here is that lambda, did I say, yeah. Lambda prime, did I put it? Yeah, lambda prime minus the original lambda is some constant in here, which is h over mc times 1 minus cosine theta. This is the experimental data. In other words, the frequency, the wavelength has shifted toward longer wavelength. Okay, by this amount. Obviously, this amount is small one, h, which is 6.626 times 10 to the negative 34. The mass of the electron, m, this is for the electron, is 9.1 times 10 to the negative 31 kilograms. And the speed of light, c, is equal to 3 times 10 to the power 8 meter per second. If I plug in these numbers, the ratio 6.626 times 10 to the negative 34 divided by the mass of the electron, which is 9.1 times 10 to the negative 31 kilogram times the speed of light, which is 3 times 10 to the power 8. And if I work these numbers, the powers, first of all, I have negative 34 and negative 31, I have negative 3 in here. And 8, when it goes up, it's going to be negative 11. So I have 6.626 divided by 9 times 9.1, that is, times 3 times 10 to the power negative 11. Of course, it's going to be in meters because this one is in joule second, the numerator. So it's a joule times second divided by the mass, which is kilogram, divided by the speed times the speed, which is meter per second. So that's the speed of light. So if I plug in the numbers again, joule is force, which is kilogram meter per second squared times meter times second divided by, so this is your joule, divided by a kilogram times meter per second. Well, the second and the second squared cancel, and then meter per second and meter per second cancel, the kilogram per kilogram cancel, and the whole unit is in meters. So this is actually a distance, okay? Which is exactly how the wavelengths are measured also. They are measured in meters because all of these things are in nanometers. And so is this number actually is going to end up in nanometers because it's 10 to the negative 11. And that's the point I'm trying to make actually, is this number is tiny. As a matter of fact, it's worth knowing what this number is. So let me find a calculator in here and get it. Can you guys check the number in here? What is 6.626? Because you're going to need this number a lot, especially in your homework assignments and also in your exams. So it's a good number to know. So it's going to be 0.2427 times 10 to the negative 11 meters. Usually we write this one as 2.427 picometers because 10 to the negative 12 is picometer. Okay, this number is tiny, and for wavelength in that order, it's significant because when they are small, when lambda prime and lambda are of that order, then in this case, the difference between them is significant. But when lambda is in this range, for example, in 100 nanometer, then in this case, the difference between these two numbers is tiny. That's why you don't see it for the case of, for example, the UV or even the visible light or even the long wavelength. So you can't really see that except when you are dealing with short wavelengths. So when you're dealing with short wavelengths, the Compton effect, which is that what we're talking about in here, becomes significant. So it's significant only in the range for X-rays and probably gamma rays. Okay, makes sense?
Yes.
Okay, so this is an experiment. But Mr. Compton, of course, knew about the theory of that was developed up to this point. Are we doing the same thing with the internet again?
I think so.
Can
It
you
keeps
guys hear
cutting
me?
out.
Sorry about that. Okay. Anyway, so this is a collision. So you have a particle that has a momentum p, a particle that has a momentum pe, which is really a particle. This one, there is no question about it. So this is the angle where this, I'm sorry, I called it theta, okay? What theta? Okay, let's use theta. I think the book uses the theta 5, so that's why I was, but most of the time you find it in the literature as theta. So it doesn't matter. So this is the angle theta that we're talking about, okay? So which we're looking at this thing. So we have, in this case, collision between three particles. So what I'm going to say in this case is the momentum before, which is just of the incoming photon, because the other one is considered on average to be standing still, namely the electron. So it must be equal to the momentum of the outgoing photon plus the momentum of the electron. Makes sense, this expression for everybody? This is conservation of momentum.
Yes.
Okay. The other expression that we're going to do in here is the conservation of energy. So the energy before is that of the photon and the electron, and the energy after is that of the outgoing photon, because this one is gone, and that of the electron. So the photon was, the electron was standing still. So the only energy that it had on average is, so basically this is what I'm going to say for the electron before. So before, for the electron, it was square root of mc squared plus 0 squared c squared, because it was not moving on average. So this is just the energy before of the photon, mc squared. Okay, where m is the mass of the electron. Okay, but the energy for the photon before, the energy for that photon is going to be equal to h times its frequency, or h, and the frequency, remember, f times lambda is equal to c. So the frequency is actually c over lambda. We're going to express things in terms of lambda all the way through. So this is hc over lambda, okay? Because we need an expression that involves lambda at the end, because this is the experimental law. This is what we found by experiment. So what we're going to do in here, actually, we're going to plug in the value of the energy for the photon before. The energy for the photon after, if you're curious about it, is simply, so this is 1, if you wish, this is after. It's a new photon now that came out, and it came out with a new frequency and a new wavelength. Okay? The energy for the electron after, so the energy after is simply equal to, again, its rest energy, mc squared, plus now it has a momentum, p squared, t squared. So the photon, the electron now is moving in a different direction. So this is all the expressions we have now. So we're going to say the energy before, which is these two quantities, must be equal to the energy after, which are these two quantities. So that's the total energy before and the total energy after. So what I'm saying in here is that mc squared plus hc over lambda, or I'm going to write it as pc if you like, okay? Because this is the same thing as pc. because P is h over lambda, where P is the momentum before, but not as a vector because the energy is scalar. The same thing in here. I can write this one as P prime C. We can write this expression in terms of momenta. So if that's the case, then that's just plus BC for the electron before is equal to the energy after, which is P prime C, the energy of the outgoing photon, plus that of the electron, which is mc squared, the whole thing squared, plus the momentum of the electron squared times the velocity of light. So again, this is from a relativistic perspective because these energies are high. We will see if relativity now, if at the end these energies will become for the electron relativistic or not. That's not the issue at this point. So we're going to solve these equations because we have PE from the first expression equals to P minus P prime. And this expression involves, of course, P and PC also in this expression. So I'm going to write the expression of the energy. By the way, this is how you deal with the energy most of the time in relativity. So I'm going to leave the square root by itself. C squared, what is C prime? Must be equal to, again, I'm going to collect these two terms in here with light. So it's P minus P prime times C plus mc squared. So I moved the P prime to the other side. It became negative. Okay. To deal with this square root, we usually square it. So if we square both sides of the expression, so I'm going to end up with mc squared plus PE squared times C squared. On this side and here, I'm going to square the whole thing. So I'm going to end up with the square of the first one, which is P squared T squared, plus P prime squared C squared minus 2P P prime C squared, okay, plus the square of the second one, which is MC squared squared. And I have a cross term in here between the MC squared and the other two quantities. So I have plus 2P times M C cubed minus 2P prime M C cubed. If I didn't forget any terms, that's everything that you have from squaring everything in here. Obviously, MC squared cancel from both sides. Sounds good?
Yes.
Okay, so we're left with this P squared of the momentum for the electron equal to the rest of the terms that don't have that mass term in here for the electron. At least the energy, the rest mass of the energy, the rest energy of the electron. So what we have in here, we have P squared, C squared, plus P prime C squared, P prime squared C squared, minus 2P P prime C squared, plus 2PM C cubed, minus 2P prime M C cubed. Now we can get rid of the C squared also from this term and this term and this term, and I have a cubed in here, so I will be left with a power of 1, and I will be left with a power of 1. So the momentum now that is left for the electron squared is going to be equal to P squared plus P prime squared 2M C minus 2P prime C MC. Oh man, this internet thing today is giving me a headache. Big time. Let me go back into this vector relationship. I'm going to square that relationship. So square it. So that gives me P squared, PE squared on this side. And basically, when you square a vector, you multiply it by itself, okay? So what I mean by P squared is just PE times PE. And that is equal to P minus P prime times P minus P prime. Okay. Obviously, P times P is P squared. And then minus times minus, that's P prime squared. But I have in here the cross product, which is, and remember the dot product is it's basically, what is it? Yeah, commutative. So you can change the order, it doesn't matter because it's a cosine of the angle between them anyway. So it's -2 times P prime times cosine of the angle between P and P prime. And that's exactly theta. You guys look at the geometry that we drew earlier. That is the angle between P and P prime. P is going this way and P prime is going that way, so it's just theta. So it's just cosine of theta. So PE squared then is equal to P squared plus P prime squared minus 2P prime cosine of theta. Okay. Now if I plug in PE squared in here, then I will have an expression. Remember, the first side of that expression is P squared plus P prime squared minus 2PP prime plus 2PMC minus 2P prime MC is equal to P prime, PE squared, which is P squared plus PE prime squared. I'm rewriting the expression for PE because that's the same term in here. Minus 2PP prime cosine of theta. Well, the P squared also and the P squared also cancel, and the P prime also and the P prime squared cancel. So I'm left with the following. I have, and the other term that is going to cancel is the number 2 from both sides. This 2 and this 2 and this 2 and this 2. Okay. I'm going to take this term here that has the cross term, which is PP prime. So it's going to change sign from a negative becomes positive, and we're done. So what I have at the end, so the 2's are gone. So I have a PMC minus P prime MC is equal to P times P prime. Remember, the 2 is gone, okay? And I'm left with a positive 1 in here minus cosine theta. We're almost there. All we have to do now is sub the values. This expression is important as is, okay? So we'll need the momentum at some point. So when you are doing your homework problems, you don't really need to rewrite this expression because you can already use it, okay? So this is important. But what I can say in here is that the momentum of the incoming particle is h over lambda. Did I have a term in here that is not supposed to be in the... yeah, h over lambda times mc minus h mc, this same mc, divided by lambda prime is equal to the product of the two momenta, which is h squared over lambda prime times 1 minus cosine theta. Obviously, the h squared and the h cancel. So I'm left with an MC, and this is what we do normally into this expression. We multiply it by lambda prime and divided by MC. So this MC is gone because I have it in the denominator. This lambda is gone because I have it in the numerator. So I'll be left with lambda prime in here. Did I write the expression? I think this is wrong, okay? Yeah, that's correct. That's correct. Everything is fine. So this leaves me with lambda prime, because again, the lambda and the lambda cancel, and the MC and the MC cancel. So I'm left with an lambda prime in the numerator. And in here, I'm canceling MC from the denominator with the MC from the numerator, and canceling the lambda prime with the lambda prime, and I'm left with a lambda only. And this term, I have an H that is left from canceling the H squared, so I have 1. And I'm dividing by MC. And the lambda prime, both of them cancel because both of them are in the numerator and denominator, 1 minus cosine theta. So this is the theory, and it's all based on the fact that the wavelength and the momentum are related to one another through this expression. P is equal to H over MC, H over lambda. So the fact that the light, which is typically a wave, has lambda wavelength, now has momentum. So we use that expression now into this one, and we already found basically the fact that the experiment matches the theory. And it only does so because light behaves as a plane particle in a collision. You guys see where we're coming from now, where we are at?
Yes.
Okay. So we started with a wave, which is what Mr. Young experiment did, if you guys remember from your physics 2 class. You take light, usually it's indivisible, that's the original experiments, but you can take it of any frequency, even those high frequency ones, even the short wavelengths. And you run it through a slit, and you're going to produce the difference patterns that you normally produce. So it's going to be a very high intensity in the center, dark fringe in here, then another one in here, bright fringe, then a dark fringe on top on the bottom, and so on and so forth. So this is wave. And you can measure the wavelength by measuring this distance, how far the slit from the screen. So that is L, and you find the angle with which you find this distance basically for the dark fringe. So this is your Y. The ratio of Y over L, that is for the small approximations, is actually the angle in radians. And from there, you do the experiment and you find the dark fringe is, if you guys remember from your physics 2 class, is related to, so it's going to be what? A, which is the opening in here, A times sine of theta is equal to, for the first one, namely M equal to 1, is exactly equal to lambda, the wavelength. So if you know the opening for the single slit, and you can measure theta by just doing the ratio of Y over L, which is the ratio of theta, sine theta is approximately equal to tangent theta, which is what I'm measuring by Y over L, which is exactly theta, but theta in radians, not in degrees. Then in this case, you have theta from the experiment. You know what A is, you can find what lambda is. So it's a wave. This is Young experiment. Actually, you can do it also with the double slit, if you guys remember. For the double slit experiment, you have two openings separated by distance d, and again, you produce the different patterns in here that are, you have a bright followed by dark, followed by bright, and so on, so from the top, followed by dark, followed by bright, and so on and so forth, and the bottom. Again, you go from center to center, and you're going to find the angle in this case, except that the angle now has to do with d, namely that d times sin theta is from bright to bright, not bright to dark. In this case, it's from bright to the dark in the single slit. And that too is equal to lambda for the first bright in here, from the top or the bottom. It's complete symmetry. You guys remember this experiment that you did in physics 2?
Yes, I remember.
Yeah, so this is basically the of course, if you do dark fringes has 1/2 of lambda in here because they cancel for the double slit. And this is basically what you have done. You did actually also something else, which is the diffraction grating. And I have one in here somewhere. Basically, where you run light, all of these experiments assume that lambda is the same, unique, meaning that monochromatic beam. Same thing in here, monochromatic beam. But if you don't do that, you can send a white light, if you wish, all of the spectrum, and have it go through diffraction grating in here, and then that's going to be broken down into the different colors. First of all, the central beam is going to be white. All of the beams will be in the center, but then you have to start to break the light into its components. Depending on the material that sent it, if you have an element in here of hydrogen, for example, you're going to only have certain colors that you're going to have. You're going to have what? The red line, then a blue, then 2 violets, and then there is another one that is probably going to be faint, but it's in there too. But you're going to have different materials will have different. So this is the diffraction grating. Did you do that too? You did it with the, yes, no, maybe? You guys remember this?
The term sounds familiar, but to be honest, I don't remember.
Yeah, this is different than the first 2 experiments because this one involves white light, or at least more than a single frequency. So when you send a bunch of frequencies, they get separated using diffraction grating. Okay, it's basically, if you guys have, if you notice, for example, after the rain and the sun comes out, on the water that is sitting on the parking lot, for example, has all kinds of frequencies. It's like the red light and all of that, or especially if there is oil underneath. Okay, there is oil from the car, and then there is a little bit of water on top of it. You will see the diffraction. Or you take, for example, your CD from CD or DVD and angle it with a different light, which is a clear white light, and you see all the different colors start to show. That acts as a diffraction grating because it has granulations actually in it, and that breaks the light into the different components. So that's the same experiment, same idea behind it. So sounds fun?
So fun.
Sounds familiar? Yeah, sounds familiar first what I'm talking about or not?
Kind of.
Okay. If not, if you have a CD at home, play with it today and look at the different lights. The point being in here is light is no longer doing that in this experiments. Oh man, the internet again. Light is actually behaving like particles all along. And this is the proof for it. Compton effect is a proof. Albeit for extremely short wavelength, high energy ones. Because as I was saying, this number H over MC is of the order of 2.42 times 10 to the negative 12 meters. So if I have a white light, if I have a visible light, the difference between the two will be tiny because of this factor. So 700 nanometers, and if you want to shift it, it's going to be basically 700 nanometers. It's not going to change. Even for the shortest wavelength that we can see, for example, 400 nanometers, still too high. 400 nanometers is, let me compare the two numbers. Okay, what is the number that we found earlier? Here it is, 2.427 picometers versus 400 nanometers. 400 nanometers over, what is it, 2.427 picometers is nothing, because this one is 400 times 10 to the negative 9. It's not nothing, it's a huge number. Actually, because we will not see the difference between the two. That's the point I'm trying to say. Divided by 2.4 times 10 to the negative 12. This is 10 to the power 3 when you move the 12 to the other one. So it's 400,000 divided by 2.4, which is 200,000 times bigger, okay? So even this is the shortest, the violet wave frequency. So it's 200 times smaller. So the difference between these two numbers is extremely small. I mean, it's probably, you're not going to notice it from the violet light. But for the X-ray, which are in this order, then you're going to definitely notice it. Or the gamma rays, which are even shorter than the X-rays, then you're going to definitely notice it, okay? So this is why light is actually, this Compton effect, you're going to notice it only for this one. But the other one, the photoelectric effect, you're going to notice it even for longer wavelength, namely in the UV range, or even the visible range for some materials. So light behaves as a particle all the time because of this phenomenon. So the question that now that begs to be answered is, what is light? Is light a wave or a particle? And that's a legitimate question because waves are not particles. If I take this rock, for example, it's definitely a particle. If I bring another particle, for example, let me bring this battery, I cannot put them together so that I can make something bigger out of them. They're separable all the time, no matter how they interact. They collide, they do all the conservation of momentum and all of that stuff, but I cannot do something like, for example, interference patterns, where I take a wave. That's exactly what the double slit and single surface experiments are. If I take a wave, for example, and another wave and add them, I'm going to have constructive interference, or I could end up with no wave at all. They cancel each other if I have destructive interference. So if I come up with this amplitude, and that's why I was seeing the dark fringes in the single experiment. I cannot do that with particles, so it's impossible. So in this case, the question is light wave or particle? And the answer to this one, it depends on what experiment you have. So light has a dual nature. Light has a dual nature. So it depends on the experiment that you do, really. you're doing the wave type behavior, you're going to find it behaving as a wave. And this is completely different than a particle. Okay. If you do another experiment, you're going to have it behaving as particles, like what we were talking about, this effects that we mentioned. Then in this case, then it's a particle. Okay. So sometimes it shows you one side, and sometimes it shows you the other side, which seem to be antagonists to the two sides are completely against one another. But that's exactly what's happening with the wave, with light. Okay, behaves as both. Okay. So that's what we're faced with in the beginning of the 20th century, around 1905, the experiments of the photoelectric effect, and around the 1920s with this effect, and actually between them or actually before that, how light was produced using, X-rays how produced using the Bremsstrahlung approach, namely the breaking or the break radiation and all of that. So at that point, light seems to be confusing things. People didn't understand what's going on. Let me finish this thing with the Heisenberg uncertainty, and I'm going to explain it, because I cannot really prove it honestly, because we don't have enough algebra to do it. Okay, here is the idea behind it. Let's go back into the single slit experiment. Okay, in the single slit experiment that you guys did from physics 2, you have light that is run through an opening A. So this opening is A, basically the spread in the y direction. So if I want to make light as narrow as possible, I would want to have A as small as possible. Do you guys understand? So I can zoom on it. I can make a very narrow light in here by making A extremely small. I call this spread in here, it's in the y direction if this is the x direction. So this is the x direction, this is the y direction. So the spread in the y direction is A actually, that is delta y. If I open A too big, then the beam of light can go everywhere in that direction. If I make it narrow, that means it's as small as possible. Okay, so this is point one. When light goes in, it's going to scatter in such a way that the first fringe, the first dark fringe actually that's going to form is at a distance in such a way that A sine theta is equal to lambda. Typically, it's m lambda, where m is more than 1, 2, 3, and so on and so forth. Those are the numbers that you did. But the first dark fringe forms exactly when m is equal to 1, where m is the number of the dark fringes on top, or on the bottom for that matter. It's going to go up and down, okay? So there is a spread now. You started narrow, now it's going to spread, okay, in this range. Remember, sine theta is still a small angle. So sine theta is theta. So this expression tells me that lambda is roughly of the order of A, lambda over A. And A, I'm arguing, is how narrow I can make that opening. So I'm going to call it delta y. The spread of the beam in the y direction. Obviously, I would want to make that one as small as possible, okay, to make sure that there is no spread. But then, if I do that, theta becomes big. In theta, the particles, when they come in here, remember they have a momentum P in the x direction that is equal to h over lambda. That's their momentum. Now, all of a sudden, I find some of them in here. So that means the momentum that was in the x direction got a boost in the y direction to get them into this point. So this is the spread in the momentum in the y direction. So I'm going to call it delta, because now this is where they're traveling. The ones that hit it in here. So they get a boost, which is equal to delta py. Okay, so from the geometry, you can clearly see that theta also, or the tangent of theta, is the delta p in the y direction over p that is going in the x direction. And that p is h over lambda. Okay. This is the one we were talking about. This is the photons moving in the x direction. But somehow, some of them end up in the y direction to give me this dark fringes that form in here. And this, for the small angles, tangent theta is also theta. So these two expressions are the same. However, this is the first fringe. The spread could be more for the next ones or more. So this is the minimum that I'm going to get. So delta PY is at least this number. So that means it's greater than or at least equal to this value of theta. So the first one, namely lambda over A. And lambda over A, remember, is lambda over delta Y. Okay. It's a matter of algebra now to play this thing around, multiply by both sides. So I have delta Y times delta PY must be at least greater than or equal to lambda times P. And remember, P is H over lambda. So this number itself, P, is H over lambda. So I'm going to sub for it and cancel the lambda from the numerator and the denominator. So it doesn't matter what frequency I'm going to bring. This relationship between the momenta of that light is going to hold. So in other words, cancel lambda from lambda because P is H over lambda. So I'm going to have it H. So here is the dilemma that we're facing. If I make the arrow as narrow as possible, delta PY will become huge. I have no idea what the momentum of that light is. If I make it as narrow as possible by making it go through a small opening in here, so delta Y is small, obviously delta PY is greater than or equal to this H over delta Y. So if delta Y is small, delta PY is huge. And vice versa. If I make the momentum also as small as possible, delta Y is going to be H over delta PY. So there is an uncertainty in the position if I know the momentum, and there is an uncertainty in the momentum if I know the position. You guys understand?
Yeah.
Okay, so this is the essence of Heisenberg uncertainty. You cannot tell the position uncertainty by knowing precisely the momentum, and you cannot tell the momentum by precisely knowing the position. So both of them they seem to be interconnected. As a matter of fact, I did it. I can take the whole experiment and rotate it by 90 degrees, and this expression will become in the x direction. So the delta x and the corresponding momentum for it must be greater than or equal to h. If we did treat this one more carefully, this is just to give you an idea. The correct relationship is actually much deeper than this. Delta px times delta x is actually greater than h bar over 2, not h, where h bar is h itself divided by 2 pi. Okay. Remember, h is 6.626 times 10 to the negative 34 joules second. And when you divide that by 2 pi, which is 6.28, this is roughly about 1, slightly more than 1, okay, times 10 to the negative 34. That's h bar. I mean, it has a name now. People know probably more h bar than h itself. H bar is the same h, except there is a 2 pi between them. That's all. So this is actually the more accurate relationship. And it relates the two quantities, the position and conjugate momentum. What I mean by conjugate is, don't tell me delta x and delta py. This quantity has no bearing whatsoever. Delta, the position in the x direction and the momentum in the y direction are not related. So two different coordinates are not related, okay? So it has to be delta x and the momentum in the x direction, or delta py and the position in the y direction, or delta pz and the momentum in the, or the position in the z direction. So those are the related quantities, the conjugate quantities. Okay. As a matter of fact, the word conjugate is used more accurately want to describe this one when we talk about operators and the algebra, which is Dirac algebra. So that is actually conjugation. That's going to be actually how you play the different ones. And it's actually coming from an old idea in old classical mechanics called Poisson brackets, which is also uses similar terminology. So they have to be the same direction. Do you guys understand this? So this is X, this is X, this is Y, the other one is Y. You cannot have it between something else. Yes?
Yeah, makes sense.
Okay, very good. So let me conjugate another two quantities for you guys, and namely time and energy. Remember, a wave is kx minus p minus omega t. This is typical waves in classical mechanics. K is 2 pi over lambda minus omega, which is 2 pi times the frequency times t. So these expressions that we know them, okay? This is cosine, okay? And for x equals to 0 at a specific point for a wave, well, I'm dealing with just cosine of 2 pi times the frequency times time. And the frequency that we found all along is hf. It's related to the energy. So in a typical wave, if I have more than one wave, this is just a plane wave. So if I have more than one, I will have different frequencies. But what I'm saying in here is that this cosine, the frequency itself is related to the energy by E over h. This whole argument about waves behaving like particles have this energy in it too. So F is equal to E over h. So what I'm having in here is 2 pi times E times T over h. Remember that h bar? This is what it's going to come out to. So it's E times T over h bar. Well, in this expression, because in here, x and the momentum, which is, remember also there is a relationship between lambda in here. I didn't write it, but lambda is equal to h over p. And that's where the momentum came through also from this expression. So cosine of 2 pi times x times divided by lambda, and lambda is h over p, so the p will go up. So that's also where the cosine of at least the spatial part of it has x times p over h bar. So again, this is actually where also that connection between the x and p. In other words, because this is actually a dot product, and that's why the two quantities in here, they have to be conjugate to one another. So x and p, and there is the h bar between them. Here, E and T and the h bar between them. So because of this relationship that exists between the position and the conjugate momentum, there is actually another one that involves also the energy and its conjugate counterpart, which is actually, in this case, the time. And that too has to satisfy this relationship. And those are your Heisenberg uncertainty relationship, where delta px is just a representative of one of them. Usually you have three of them in the spatial. So this is all of them. These are all of the Heisenberg relationships. This is the momentum in one direction and the position in the same direction. So x is just a representative of all of the values, okay? You can have x, y, and z. If you wish, you can write the one for y and the one for z. They are similar to this one. And there is one that relates to energy and time. So in other words, if you know precisely when the event happened, you have no idea about the energy of that wave, okay? If you know the amount of energy that that wave carries, you have no idea when that is. So there is an uncertainty also about the energy and time measurements that you consider for particles. So this is the uncertainty principle. I did not really prove it, honestly, okay? All I did was take this argument using the diffraction, and we found an upper limit, which is h. What I'm trying to say in here, the limit is actually, if we treat it properly, is much more rigorous than just h. It's h over 4 pi, okay? So the cutoff is actually less than that, okay? Well, by an h over 4 pi, and that symbol, we call it h bar. And because it happens always h, 2 pi over h, 2 pi over h in these expressions, that's where the symbol came out to be h bar from there. So we're not dealing with h anymore, we're dealing with h bar as a constant. And just with the 2 pi factor between them. Anyway, the point being in here is the energy all to one another. Okay. So, and that is where the ET uncertainty principle comes in. Makes sense to you conceptually. I know I did not do the proof because it's actually beyond the scope of this course, honestly. But I try to explain it as best as I can. Make sense?
Yes. So just a question, when we're using the equation E is equal to HF though, would we use H bar there as well, or would we just use Planck's constant?
Yeah, you can use H bar and you can use K, and we're going to come back to these questions down the road. So energy can be written as HF or H bar omega. Remember?
Right.
The frequency is just omega over 2 pi. So you move the omega to H over omega, so it becomes an H bar, but then you cannot use F. You have to use the angular frequency omega. Same thing in here. The momentum is equal to, what is it? H over lambda. So all I have to do is multiply by 2 pi and divide by 2 pi, and H over 2 pi is H bar, and 2 pi over lambda is K. So you can use H bar K for the momentum. That is the same relationship we're dealing with all along. Either use H divided by lambda or H bar times the wave number K. And the same thing with the energy being H times the frequency or H bar times omega. So we're going to come back to these expressions involving omega and K down the road. And I think chapter 40 will introduce these two big times. And they're just the same identities we've been dealing with up to this point, the same relationship we've been dealing with up to this point, except instead of expressing them in terms of H, we really need them in terms of H bar. Otherwise, short of creating an extra 2 pi times H every 2 pi or dividing by 2 pi, this expression will be written then HK over 2 pi. So instead of just dividing by 2 pi, we just absorb it in one the constants, and then it's easier to write. That's all. Okay. Nowadays, people, when they talk about Planck's constant, they really don't mean H, they mean H bar. And H bar and H are related to one another, like I was saying, with just that 2 pi in between them, okay? Just take H and divide it by 2 pi, okay? Whatever that value is. And it's the same number. Make sense? This is the question?
Yeah.
We're going to come back to this one. But here is the uncertainty, and we're going to need this uncertainty big time down the road in chapters 44 and 43 and things like that, when we see particles come out of nowhere, okay, get created and then destroyed immediately, okay? So this thing in here are important. In other words, particles will borrow a huge amount of energy from vacuum where there is no energy. As long as they return it in time, this relationship holds, then they're fine. You can have phenomena like that. Okay, chapter 39 now. So again, this is where we are right now from chapter 38. Waves that have specific lambda, a specific frequency, have momenta that says that basically h over lambda. So this is a momentum, as if it has a mass times velocity for a wave. And also energy that is equal to HF. Used it, Mr. Einstein used it, Mr. Compton used it, everybody else started using it after that, because, and it has no justification. I have no idea what this H, basically how to justify it at this point, okay? So that is one thing. Then we can, even we push the envelope further, we have actually waves having particles because of the fact that's the only way to explain those phenomena. Mr. de Broglie, this is one of the things that Feynman makes fun of the French people, because this one is French. I mean, how could you say this one de Broglie? That's how the name is pronounced, okay? The French people pronounce. Obviously, it's written de Broglie, okay? If you want to say it this way. But Mr. de Broglie, when he was working on his thesis in 1923, he proposed an idea. Okay? Actually, he didn't publish it until 1924. And the idea is the following. Nature-like symmetry. If photons behaves like, if light behaves as particle, shouldn't a particle also behave like a wave? So this light, which is a wave, behave like a particle. Shouldn't a particle also behave like a wave? So all he did was, if light has if a particle has a definite momentum p, then it will have a wavelength lambda equals to h over p. What he did was take this expression and flip it around. This is algebraically correct, okay? So if somebody had the momentum, they can find the wavelength. Does this make sense? So in classical physics, h will be just mv. If you're going to have it in relativistic speeds, if the particle is moving super fast, then lambda is simply equal to h over gamma mv, where gamma is your Lorentz factor, which is 1 over 1 minus b squared over c squared. You guys understand the proposal that he made in his thesis?
Yeah, sort of.
All he said was like nature-like symmetry. Okay? If a wave behaves like a particle, that's what we saw, shouldn't a particle also behave like a wave? So if a particle has a definite momentum, which is mass times velocity, then it has a wavelength, according to this expression. Okay? And we should be able to find its wavelength if I know its momentum. If I know how fast the particle is moving, then all I have to do is divide h by mv, and I'm done. I have a wave number. I mean, I have a wavelength. Okay? So I have definitely some quantity for it now. Okay? So this is where he proposed it, and it was basically, he published this stuff and done with it. In 1927, two people, okay? Davison and Germer, his name was Germer, okay? Davison and he's German, so usually the G sounds like a G, Germer. Okay. They were working on an experiment, and that experiment basically involves shining sending a beam of electrons, which are particles. It started first of all with Mr. Germer working on the experiment by himself on shining it on tungsten, and then later on, when he was joined by Davison, they started actually using nickel instead, and so this is basically the design. Let me share with you another screen. Let me stop sharing this one in here and share with you this screen that I found actually. Did I close that picture? Did I close it? No, it's still here. Okay, good. So this is the experiment that they were working with, okay? This is in a vacuum. So this is your nickel, okay? And they have in here an element of tungsten that is heated using the Joule heating. So you have electrons that are free in here, and you have an accelerating voltage. So this is an anode, this is pulling them with extreme high velocity. As they come out, so these are electrons now. So it's a beam of electrons. And they were looking at the nickel, and they have in here a movable detector that they can see the outgoing electrons, basically. And they were interested in the properties of the nickel in here, trying to, basically what the idea was from Mr. Germer when he started the experiment was to see if he can replicate an experiment that Mr. Rutherford did when he hit the alpha particles, which are positively charged particles on gold and silver and other metals, and detected basically the nucleus. So the idea is similar, but instead of sending positively charged particles, he wanted to send negatively charged particles to study the atom. So this is his interest. They wanted to see the properties of the atoms using a negatively charged particles to see where the distribution of the negatively charged electrons are. So obviously the electrons will be bouncing off depending when they interact. So that's the whole point that they were interested in. And this is the accelerating voltage in here. So they know the speed with which these electrons will come out. All you have to do is use a conservation of energy in this case. 1/2 of mv squared, if they are not relativistic, is equal to the accelerating voltage for each electron, which is the charge E times the voltage, and that is the potential energy that accelerated them. So they know how fast these electrons are moving. So they did this experiment, and they were fine with it until one day, by accident, air get into that chamber. The reason why they wanted air is because these are the tungsten itself is the material. Nickel itself is pure metal, and you don't want air in there. So what happened with the air when it interacted with the metal? It formed an oxide over the surface, and that was no good. So what they did, they took that material and they basically heated up so high, they melted it basically and smoothed it, and they worked on it to make it as smooth as possible, and they retried the experiment again because that's what they were after. That's what they were trying to do. The point being in here is they found diffraction patterns. They found that the outgoing electrons, they didn't know it then. When they did melt the nickel again and resurface it, they actually produced high crystalline structure. And like the previous structure, which is they take from the ore and you work it out, which is a polycrystalline random, and you have no control over the and that's why you see light going in every direction with no interference patterns. But now, since it's a crystalline structure, the cyclical atoms is fixed, and you will have spacing and you will have diffraction patterns. So now electrons, not X-rays, are going and bouncing off of the metal and producing diffraction patterns typical of waves. So they knew then, let me share with you the screen, what to do next. So in their experiment, oh man, I have to hit this back. They know what the wavelength of this, that they can measure. So they can measure lambda from their measurements, depending on the diffraction patterns that they form in them. Distances and the angles and all of that. So you can find lambda. It's not difficult experimentally. But they know also that these particles are moving with a velocity that is given by the conservation of energy, E equals to mv. I mean, E times V, the electric charge of each electron, times the potential that accelerated them, AC, is between the anode and the cathode actually, is equal to this expression. From here, you can find V, which is just the square root of 2 times E times V, the accelerating potential, divided by M, which is the mass of each electron. So you have a velocity, okay? Obviously, you need the momentum for these particles. You need the momentum, which is P equals to mv, and take M and take it inside the square root, and you're going to end up with 2M times E times D, the potential between the anode and the cathode. And that is basically how they found the momentum. So all they have to do is come back to this expression and check it. Does this measured experimental value of lambda, does it match H over this value? And it does. So that was a proof beyond the shadow of a doubt that the hypothesis that Mr. de Broglie came up with works, okay? Because this experiment, this theoretical value and the experimental value, they match. In 1927, when they did the experiment, actually, like I said, they did it by accident because they had a problem in their apparatus where they have oxidation that they didn't want. And in 1927, Mr. de Broglie actually received the Nobel Prize for his proposal. So particles now behave as waves. If you know the momentum, you can find if you know the momentum of the particle, you can find its wavelength, lambda. Okay, so this is basically something else that obviously when they're moving with extremely high velocities, this expression I used in here has to be corrected. and you have to use a corrected value. So if the velocity is high, remember the momentum P is equal to mv divided by square root of 1 minus b squared over c squared. So we have to write a different expression in here for the velocity, and we have to use a conservation of energy in a different fashion. But that is basically the expression that we're going to be dealing with most of the time in terms of homework. Okay, it's 9:20. I know we still have about 5 minutes, but the next idea from this chapter, let me tell you what we need to finish, is Niels Bohr's model for the atom. Before I do that, we need to talk about the experiment of Rutherford. I know I mentioned it briefly. And Mr. Rutherford experiment in New Zealand, when he did it, basically he detected the fact that the atomic structure now it has a nucleus and it has the electrons are on top of it. So now this goes first, okay, the Rutherford experiment. So we need to explain what's going on in the atom. So Niels Bohr came up with the atom explanation for the hydrogen atom, not any atom, okay? Okay, and it matched with the third point that we need to talk is a spectral analysis or spectrum of hydrogen atom again, and the different lines basically that form the Lyman line and Balmer line and Paschen line and all of the other lines that form. And of course, what interests, I already mentioned a few of them. I mentioned the Balmer a few minutes ago when I was talking about the different colors that form that are in the visible range. And so these ones are explained beautifully by the theory of Niels Bohr, and then that's the extent of his theory. It cannot go past of the hydrogen. You try to apply this theory to helium, it fails miserably. Okay, so that's what we're faced on around the 1910s, 1920s actually, when this whole thing came out, and that is the onset of quantum mechanics. And chapter 40 will just hydrogen in the periodic table. Okay, sounds good, everybody? Guys, hear me or not? Okay, thank you, Natasha. Anyway, the point being in here is this is where we're standing right now. We still have the Rutherford experiment, which is going to be just an experiment. Then we'll go in a little bit detail about the Niels Bohr's model, and then we work out some algebra here and there and get the different wavelengths that form into the spectrum of the hydrogen atom. And that's the extent of chapter. Okay, there is another thing in here. The argument that we presented for the uncertainty principle for the waves still holds in entire integrity for the particle. Okay, so a particle, if you don't know its position, if you know its position precisely, you don't know its momentum, and vice versa. And if you know its energy precisely, you don't have any measurements for its time when that measurement was happened, and vice versa. If you measure the time precisely, you don't know how much energy that particle has. In other words, the uncertainty principle actually is universal for all of them, whether it's light or behavior or particle, because of this duality. Okay, because of this dual nature of things being waves and particles in the same time. Okay, so around 1927, there was two basically approaches to quantum mechanics, and they're still there, both of them. The first one is that due to Mr. It's really the Heisenberg school of work, which is really based on algebra and matrices and things like that. And the other approach is the Schrodinger approach, which is really more of a differential equations up front, and both of them agree in the same results. Both of them, although in the beginning people were really fighting over it, which one is more accurate, and both of them are correct. Then after that, in the 1940s, a new idea starts to develop because there was problems with light and the quantization of the energy of light. So the quantum electrodynamics really came out, which is QED, which is a more advanced theory than this one. We're going to touch base with it probably in chapter 43, okay? And 42, 43, and then, no, 43, okay? And then we go a step further inside the nucleus where the QCD came on, which is quantum chromodynamics, which is a more modern theory than everything else. And that is actually explains what's going on inside the nucleus itself, inside not just the nucleus, inside the proton itself and neutron, inside the elementary particles. And then we come up with the standard model, which is the most advanced theory there is, short of the string theory, because the string theory is not really proven yet in Indian laboratory to be taken seriously by at least experimentalists and physicists everywhere else. So you're going to get everything that everybody knows up to this point in physics. Sounds like it's a good plan?
Yep, sounds good.
If the internet will allow us, okay? I'm sorry about these things, okay? Yeah, I will see what happens in here. Thank you, guys. Let me stop the recording.